ladies and gentlemen, boys and girls. My name is Mr. Du, and science is my business. You are welcome to Mr. Du Scienceworld. And today we are going to talk about equilibrium. Equilibrium in physics. Now let's look at it. When we talk about equilibrium in physics, what do we mean? There are two types of equilibrium that we can look at in terms of physics. We have what is called a translational equilibrium and what is called what? A rotational equilibrium. When do we have a translational equilibrium? We have a translational equilibrium if the sum of all the forces acting on an object is equal to 0. In other words, the net force is equal to what? 0. That means we can have an object that is at rest, or the object is moving with a uniform what? A uniform motion. If that object is accelerating, then we can say that the object is not a translational what? Equilibrium. As long as the object is what? Is accelerating, then the object will not be at what? A translational equilibrium. Now we are going to look at different processes or the different scenarios. So let's look at the first one and see. We can have a situation where the object is at rest and a situation where the object is not at rest. But in this case, or in this video, we are going to consider a situation where the object is what? Is at rest. So let's try with an example. Okay, so if we are at a translational equilibrium, that means that the Fnet is equals to 0. And if Fnet is equals to 0, we can look at it from 2 points if the object is also at what? A two-dimensional. So if it is two-dimensional, then what are we going to see? So we can see that first one, Fnet, is equals to 0, or if it is a two-dimensional, then we are going to see that the Fnet in the x direction is going to be 0, and the Fnet in the y direction is also equal to 0. And when we have such situation, then we say that what? We are at a translational equilibrium. Let's look at one problem here and let's see. Let's solve a problem here. Right. We have a question here, and the question is saying that in a relative simple structure, we have a 500 kg load supported by 2 cables, within which in turn are attached to a walls. Let's say that we would like to determine the force in what? In each cable. Now we are going to determine the force in each of the cables. The force that exists in a cable or in a string is what? Is the tension. That means that we are looking for what? A tension force here. So if you are looking for a tension force, let's try and see how we can find the tension force from this point. Okay. Let's try and give the diagram of what we are given. Let's give a diagram of that and see how we can solve the problem. So let's say here is our wall. We have the wall like this, okay, and there is a force from this point, and there is a force from this point, and now there is a mass that is at this point here. The mass is 500 kg. There is a tension. Let's call this one T1 at an angle of 53 degrees. There is also another tension here at an angle of 60 degrees here. Okay, good. Now we are told that we need to find the tension in the cables. So I am calling this one T1, then this will become what? T2. So there are 2 tensions that we have in there. Let's try and see how we can find these tensions. So we'll first have to draw a free body diagram for the problem. So to draw a free body diagram, all that I'm going to have is I'm going to take it from this point and draw a Cartesian plane. Okay, so let's have a Cartesian plane drawn in that way. So we have our x here, and we have the y in this direction. Now we're trying to find the forces that are acting. There is a tension here, and this tension, which is T1, is at an angle of 53 degrees. So this side is 53 degrees. And there is another tension which is on this side. That is T2. That angle is here is 60 degrees, so here will be 60 and then this will be 30 degrees. So we'll have this to be 30 degrees. Now what we see is that we can see we are having what? The weight of the object will be acting downwards here. That is the weight. So let's call that one FG load. Okay. So we have the FG load on this point here. We need to solve this problem. This is the free body diagram. If you have gotten the free body diagram for this, now let's see how we can solve the problem. We need to resolve this and resolve this also into component. And that means that we are going to find the y component here. Okay, so we are going to find y ty1. Okay, and then on this side is the x component, so that is tx1. And then on this part, we are also resolving it. So we also going to have the T2 or Ty2, and on this side, we are having a Tx2 on the side. Now let's resolve it and find the values of each of those forces that we have there. This is the angle opposite side is this, so therefore this is just simply going to be T1 sine what? Sine 53 degrees. Sine 53 degrees. And this side is just going to be T1 cos 53 degrees. And here we are going to have the sides to become our Tx2 to be equals to, this is the adjacent. So that will be T2 cos 30 degrees. And this side, we are going to have on that part, let me put it here. So we're going to have that part to become our T2, okay, being equals to what? Sine 30 degrees. Right, good. I have resolved and found all the components on this. We need to then apply a translational equilibrium to solve the problem. And how do I apply translational equilibrium rule? We are saying that Fnet in the x direction must be equals to 0. So let's look at the x component. The horizontal component for this is here. And if I look at that horizontal component, I can see that it is what? It is Tx1 and what? And Tx2. So we can simply see that the Fnet in that direction is now equals to, this side is positive and this side is negative. So I'm going to take this side to become T1 cos 53 degrees plus this side, which is negative side. So that's going to be negative T2 cos 30 degrees. And we know that this is equal to 0. So this simply means 0 is equals to T1 cos 53 degrees minus T2 cos 30 degrees. Okay. Now I have gotten this. I am going to make my T1 to be the subject. I'm going to make T1 the subject from here now. So if I want T1 to be the subject, it's like I'm transposing this. So I'm going to have T1 is now equals to T2 cos 30 degrees divided by cos 53 degrees. I will call this one equation 1. And that is the what? The horizontal part. The sum of the forces acting at the horizontal what? Part. Let's look for the sum of forces acting on the what? On the vertical component as well. And that is going to be our Fnet y. That will also be equals to 0. So what is the Fnet y? There are three forces in the vertical direction. That is Ty1 and then Ty2 and FGL. So straight away we are going to see it from there that we can see these ones are at the upper part of the what? Of the Cartesian plane, and this is positive side and this is the negative side. So I am going to have this simply to become what? My Ty1 plus Ty2 y2 plus the what? The weight part, which is the FG load. Now let's try and put in the values and let's see what we're going to have. This is 0 is equals to Ty1. Our Ty1 is equals to T1 sine 53 degrees plus Ty2. Ty2 is giving us T2. Okay, so that is T2. We are having that to become T2 sine 30 degrees. T2 sine 30 degrees. And what is our what? Our FGL. Our FGL will now become negative 1, mg. And that has given us the expression that we are looking for. Now, from this expression, let's go and substitute T1 from the equation 1. So this has become my equation 2. I am going to substitute T1 into the equation 2. So, substitute T1 into what? Equation 2. And if I want to do that straight away, what am I going to have? I need to do the substitution. So this is 0 is now equals to T1 is here, and that is T2 cos 30 degrees. Okay? Cos 30 degrees divided by cos 53 degrees. That is T1 multiplied by, that is sine 53 degrees plus T2 is here, and that is sine 30 degrees minus our mg. Now we can see that we have everything in terms of what? T2. So we can solve for T2 now, from this point now. So let's put the substitutions, let's put the values there and work out what our T2 is going to be. Let's put that into the calculator. We are having cos 30 divided by cos 50 degrees. Okay, so we have that. And we are having sine 53 degrees plus sine 30 degrees multiplied by the T2 out there. If I solve that straight away into the calculator, then we are going to see that our T2 is going to be 2971.50 newtons. 50 newtons. Now, let's leave it in the correct sig. That's going to be T2 is now equals to what? It's going to be 3.0 times 10 exponent 3 newtons. And that is the what? Is the tension force or the tension in the what? In the rope 2 or in the cord 2 or the cable 2. Now we need to find the tension in what? In the cable 1. We have seen that the T1 is expressed in terms of what? T2. So we can come to that equation 1 and substitute T2 into the equation 1. So we will go on straight away, and that is going to be T1 is now equals to T2, which is now giving us 2971.50, and we will multiply that by cos 30 degrees, and then, cos 30 degrees. So we are multiplying, or let's use this, multiply by cos 30 degrees, and then we are going to divide that by cos 53 degrees. And let's see what is going to be the value of T1. So we are going to just put in the values that we have, okay, and then let's see what we are going to have. Once we do that, we are getting that to be 4276.05 newtons. Let's leave this in the correct sig, and that is going to be T1 is equals to 4.3 multiplied by 10 exponent 3 newtons. This is also the tension in the what? In the cable 1. So we've been able to find the tension in cable 1 as well as the tension in cable 2. So whenever you are given such a problem, all you need to do is try as much as possible, resolve the forces, and then apply the translational equilibrium rules, and then use that to solve the problem. Thank you very much for watching this video. Please, if you have not subscribed to our YouTube channel, do subscribe to our YouTube channel and then click on the notification bell so that anytime that we release any new video, you'll be the first person to watch it.